All right, seems like a good time to get started. So, what we know about vectors, which is already a pretty decent amount, certainly what they are is a pretty big step, includes the following. One, we can add two vectors together. Graphically, it simply means you follow one and then you follow the other and end up at a new point. We're going to need this later, by the way. Two, vectors have size, which is simply the distance along them. And three, you can multiply vectors by numbers, but multiplying a vector times another vector, haven't done that yet. Multiplication in terms of numbers is pretty easy to describe. If I say, what's 3 times 10, you would say 10 times 10 plus 10 plus 10. If I was to say, multiply this vector times 3, you would simply add the vector to itself for a total of 3 copies. But multiplying loses a lot of its meaning when it's not simply the same thing stacked on top of itself. Simply put, vector times vector doesn't exist because of what vectors are designed to do. That's not specific enough. In fact, there are two effective equivalents of vector times vector. We're doing one of them today, and we're doing the other one tomorrow. After we have them both, we'll explain the details of exactly what it is they're used for. Yeah, word problems. So today, Friday. Just to make a note, times isn't good enough. We'll start with the appropriately named the dot product. And yes, writing it with the dot is mandatory. Writing it with an X multiplication sign, well, again, that's an entirely different process. We'll see that Friday. And simply writing them back to back is garbage. So yes, you do have to write that dot. The dot product, named for the symbolic notation, doesn't really describe what it's doing, so it takes a little explanation. The dot product is a numeric measurement trying to tell you how closely aligned two vectors are. The closer they are to pointing in the same direction, the bigger the dot product will be. The closer they are to pointing in completely opposing directions, the smaller the dot product will be. The dot product has actually got a bunch of different geometric and physics applied geometry like values based purely on that. It's basically how close, numerically, how close are these two to working with each other. With that in mind, here, therefore, is the formula or the process by which the dot product is calculated. The dot product has the same approach regardless of the number of components, the number of effectively coordinates in the system you're using. But of course, we're going to be sticking with 2 and 3 dimensions. We're not yet ready for time to travel, and one-dimensional math is just a straight line. So the only vectors are just which direction. And the dot product of 2 vectors is very easy. It is simply the product of all of the components in order. The leading 1 times the leading 2. The second 7 times the second 4. The dot product of these 2 vectors is 30. Not everything in Calc 3 is impossible. Some of these are really not that bad. Obviously, this is a tool that we'll use, but that calculation, pretty simple stuff. And again, more dimensions doesn't change it, even though, again, there's no realistic reason for us to throw in a 4th dimension. We could if we wanted to. 3, 1, 6, dot, 2, minus 5, 2. It's just product, product, product in order. 3 times 2, 1 times minus 5, and 6 times 2, which of course is 6, minus 5, 12, well, plus 12, I guess, which is 13. Now, I will freely point out that unlike a lot of things that you've done in the past in mathematics, simply glancing at a number set up like this and trying to estimate the result is quite awkward indeed. Vectors are mostly used to demonstrate where things are going, more so than the other way around. So looking at these, is there a way to tell these are correct? Not so much, no. Which is why what they do is so important, because that what they do actually explains better what this thing is in the first place. Here's what I'm talking about. It honestly doesn't matter if this is a 2-dimensional space or not. 2 vectors create a 2-dimensional space. You can, whatever direction 2 lines are pointing, you can put something flat on that angle, and you've got a 2-dimensional space. What angle is formed here? Now, here's where the dot product slowly starts to make more sense. Here's where it starts to actually have some meaning. As I said before, the dot product is a numerical calculation for how closely A and B are aiming in the same direction. The smaller this angle is, the closer aligned they are, and the dot product should go up. The further apart they're aiming, the less aligned they are, and the dot product should go down. What else does this? Cosine. The smaller this angle gets, the bigger cosine gets. The bigger this angle gets, the smaller cosine gets. The measurement of this angle can be put into the following context. The dot product is the size of the 2 vectors. That's a little clumsy. Let me try that a little bit clearer. The magnitudes of the 2 vectors times the cosine of the angle between them. Number, number, number. Magnitude, magnitude, cosine. If the two vectors are pointing in exactly the same direction, cosine becomes 1, and the dot product becomes the biggest it can possibly be. If the angle gets wide, cosine drops, and this drops with it. And just to make this clear, in case anyone is asking themselves, what if the angle is super wide, like this? Well, believe it or not, because, again, we've had this talk before about does a negative direction mean it's going in a different direction? And again, technically the answer is no. A and B are actually fairly closely aligned. Now, are they pointing in opposite directions? Yes. Will the dot product be negative to prove they're going in opposite directions? Yes. But it'll be a bigger value because their directionality is actually pretty close. You just have to understand that you might have a negative value. It is because the dot product is so heavily related to how closely these two guys are working, how closely they are related to this angle between them, that the dot product is also called the inner product. These are synonyms. The biggest difference, how far advanced the physicist you're talking to is, and possibly which country they went to school. They are the same. Ends that discussion. But it has a third name. As we've already discussed, the dot product is just the products in order of the components of the vectors individually multiplied. The dot product is a number. It is not a vector. It is not a direction. It's closest to being a distance. In fact, that's one of the ways they're basically described. The dot product of A and B is basically how much does A project along B? And when we get into word problem examples, you'll see more of how that happens. Next week. Basically, A is trying to go its own separate way, but it's going partially. Again, its projection, its shadow is along vector B also, because you can't go this way without at least partially going this way, just inefficiently, just not using the entire length. And the dot product discusses this. Moving on. As I was just saying, because the dot product of two vectors is a number, we know what numbers are called when it comes to vectors. That is why the dot product is called the inner product, is called the scalar product. Because a number, when you're talking about vectors, is called a scalar. The single biggest use of the dot inner scalar product is, again, any problem in which how closely aligned two vectors are comes into play. We'll see more of those word problems soon enough. But that means that knowing how closely aligned they are, how closely one of them is going along the other is a big deal, which is where this next term comes in. Let me switch colors. Component. To put the angle I had before back on the board, so here's vector A, here's vector B, as I was saying, part of A does follow along B. The rest doesn't, but part does. You could, to a large extent, say, what part of B do you need to make A? What part of A is caused by B? The problem is length. If B goes here, 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 or even here, it's all talking about the same direction, but clearly those different lengths are going to affect the inner product. That's not what we want. We want to talk about the direction, so we can factor that out. The component of A along B, in other words, this part, effectively, this red length, comp BA. There's its summarized notation, is basically just a very specific dot product. A dot product that only cares about the direction of B, but not its magnitude. But we already know how to fix that. We already know how to put things in B's perspective. A unit vector. If we want to take B's length out of the equation, we'll simply make a unit vector whose size is therefore 1, whose magnitude is therefore 1, and take the dot product with it. And that is what the component is. It is a dot product of vector A, whatever that is, just vector A hanging out by itself, times the unit vector in the B direction, which, as we saw last time, pretty sure it was last time, is B divided by its magnitude. This dot product is a number. This magnitude is a number. Therefore, the component is a number. And once again, this filters the size of B out of the equation. We care about how A is going in the B direction, not how many chunks of B it went in the B direction. Basically, if we were to put crosshatches on this, where every single one was a length of 1, but pointing in the direction B says, regardless of how big B really is, regardless of how far it really goes. Now, before we do this one, let's take a quick look. 4, 1 is 1, 2, 3, 4, 1, pointing in this direction. Let's call this A. 3, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is pointing in this direction. We are asking about what part of A, right angle, is pointing in the direction that this guy is pointing, not whether it gets to the end. We already know that answer is no. But what part of this is pointing this way? If this sounds like kind of a Pythagorean thing, if it sounds like we're trying to find the legs of a right triangle based on its angles, it's because we are. These things are actually very triangularly related, as we'll see more of shortly. Now, We can do the dot product first and then divide by the size of B, or we can turn B into a unit vector and then do the dot product afterwards. It doesn't matter. They'll both work. I think it'll be much easier to divide last, so I don't have to multiply by whatever weird decimals and fractions show up. So I will do that. What is A dot B over the magnitude of B? Well, we need A dot B first, but that won't take long. That's not bad at all. What is A dot B? It is 4 times 3, that's 12, plus 1 times 10, obviously that's 10, 22. What's the magnitude of B? Well, again, that's Pythagorean formula based on this giant right triangle. What is the magnitude of B? It is, again, the same as the distance formula. 10 squared is 100, 3 squared is 9. And there is the component. This is component along B of A. Incidentally, since the square root of 109 is about 10.5, this is slightly higher than 2. Side effect, this red length is slightly higher than 2. I never even told you what the angle was, although I did give you enough information to find it. And you already know one of its 2 legs. By the way, can you do this backwards? Of course you can. Do the answers match? Of course they don't. Because which vector's size has become irrelevant, have just swapped. So yeah, this is a big difference. Component AB is not going to be the same thing because we're looking at something different now. We're asking if this was projected down along this line, how much of it would be there? And this is much larger. If I were to draw a right triangle, it's much bigger. How much bigger? We can find out. Once again, the component is the dot product. The difference is the direction of this guy matters, but its size does not. This guy is the guy that turns into the unit vector. This guy is a guy whose magnitude is divided. It's even written as a subscript to help remind you it's in the denominator. Now, we already took the dot product of these two. Swapping that order does not matter because you see each of the components just swaps their order in which they're being multiplied, but that doesn't change anything. In fact, the dot product obeys the commutative property. But this we need. This we don't have, but we can find it. What is the magnitude of A? It is the same thing in concept. It is the distance formula. 4 squared is 16, 1 squared is 1. So this stays 22. It was 22 before, it's still 22, but now it's over the square root of 17, which is slightly higher than 4. Side effect, this red line is slightly longer than 4. Again, I didn't tell you the angle, although, again, you have the information to find out, and you know it's the same angle. and you were still able to find out this leg. And of course, you can find the other one if you feel the need to do so, because you have this side, and it's a right triangle. It's always a right triangle. Once we start talking about this sort of thing in any number of dimensions, a special pair of terms begins to appear. Orthogonal and orthonormal. These are big terms when it comes to talking about vectors, and now we can talk about them here. Orthogonal refers to two vectors that are effectively perpendicular. That there is a right angle between them. So why don't we just call it perpendicular? Because orthogonal has many choices. Perpendicular does not. If I draw any flat vector along this board in any direction I want, some of these may or may not be perpendicular to each other. They're all, however, orthogonal to this, 90 degrees coming out of the whiteboard. Every single one of these angles is a 90-degree angle. This marker is orthogonal to all of these, even though these are not necessarily perpendicular or orthogonal to each other. So orthogonal is a more generalized term that includes perpendicular and so much more. We're wandering out of two-dimensional stuff. We're going to need non-two-dimensional names. The idea is the same. They make a right angle. But in two-dimensional space, there's only one way to make something perpendicular, because only one line that hits it at a right angle. Orthogonal, you have a literal infinite number of choices. In any direction that forms a 90-degree angle, it's orthogonal. And again, to make this clear, orthogonal does not translate. If this line is perpendicular to this line is perpendicular to that line. If these two are orthogonal to this marker, what's the relationship between each other? No idea. None whatsoever. Now, the textbook author doesn't talk a lot about orthonormal, but it's a very easy term to throw in case we need it later. Orthonormal means they are not only orthogonal, but they're also unit vectors. Orthogonal vectors are perpendicular, effectively. Orthonormal are perpendicular unit vectors. This is pretty heavily restricted. We may see it in parts of this course. This is very generalized, and we're going to need it a lot. So, helpful but restrictive subset. All right, fine, you say. They are orthogonal if there's a 90-degree angle between them. Well, how do we know that? Well, that's actually pretty easy to do. As we've already said, the dot, scalar, or inner product is the same as the two magnitudes of the two vectors times the cosine of the angle between them. If they are orthogonal and therefore perpendicular, what does the dot product have to be? What is the only answer? Again, if they're orthogonal, they're effectively perpendicular, which means that this is what? You're on the right track. In fact, you're basically there. Yeah, if they are at a right angle, then these are irrelevant because this is 0. The dot product of orthogonal vectors is 0. You may think of that as the definition. It may as well be. I like the description better. That's what it is numerically. That's what it is symbolically. Which means it's pretty easy to check. Let's start with a positive case. Let's start with a case that will work. Vector A, I can't use capitals for that. Vector A is 4, 4. Vector B is 2, -2. Effectively, A is tracing along, let's make that a better A, is tracing along y equals x, and B is tracing along y equals -x. These look perpendicular. Their slopes, plus and -1, multiply to -1. They are perpendicular. Their dot product had better be 0, or this is garbage. But that won't take us very long. The dot product of A and B is, like all dot products, very simple to do. The chain multiples of the coordinates effectively in order. This 4 times this 2 plus this 4 times this -2. And big surprise, that's 8 minus 8, which is 0. Yes, the lines are perpendicular. Yes, the vectors are orthogonal to each other because their dot product is 0, or the other way around. Their dot product is 0 because they were orthogonal. Now, again, think of it this way. If I wanted to project A along B, if I wanted to look at A's shadow cast on B, where is it? This is a right angle. It's not going along B at all. It's going in completely the wrong direction. It has a 0 distance in B's direction. It's not going in B's direction at all. So you can think of it that way too. It's the same thing. Now let's try a negative case. Let's try a case that shouldn't work. What is A dot C? Is it 0? If A and C are going the same way. C is now 10, 1. Now, as you can see, these guys are going in a similar direction, not opposite directions, not perpendicular at all. These lines are not perpendicular. Therefore, those vectors can't be orthogonal. They can't. Well, let's go ahead and prove it. What is A dot C? It's 4 times 10. Obviously, that's 40. Plus 4 times 1. Obviously, that's 4. That is a dot product of 44, which isn't 0, and therefore not orthogonal. So it's very easy to check. 0 is pretty easy to check for. Now, since we know they are not orthogonal, we know that the angle between them is therefore not 90 degrees. Based on this picture, it looks like it's not a very big angle at all. Can we find it? Yes, let's find it. Once again, the dot product is the magnitude of the two vectors times the cosine of the angle between them. We know, let's go ahead and make it C. Erase that in your notes if you already wrote it. This should be C. I mean, it's still true. Just we're doing this specific guy, that's all. We already did this dot product. I just erased it. It's 44. What is the magnitude of A? Distance formula. Pythagorean theorem. Square root of 4 squared plus 4 squared. That's 16 plus 16. That's 32. You'll notice I didn't bother to reduce that, even though you clearly could. Generally speaking, I don't like reducing square roots halfway through a problem, but in these cases, I like it even less. Moving on. What is the magnitude of C? Distance equation, distance formula, 10 squared plus 1 squared. 10 squared is 100, 1 squared is 1. It is the square root of 101. I mean, that's not bad. Will simplifying help? What 16 root 2 root 101? You still have 2 square roots. Now, we'll finish the problem in a second, but what could I do instead? Well, I'll tell you what a lot of people do instead is find these as decimals. Considering the very next step, I kind of agree with that. That sounds like a pretty smart idea. But what else do we know about square roots? They multiply. What is the square root of one thing times the square root of the other thing? The square root of them multiplied. Yes, you can just flat out multiply right on through. And since we're probably going to find the result as a decimal anyway, why not just do 1? Why bother simplifying? I mean, can you write down the answer by hand and then simplify it by hand? Sure, but that doesn't really hand you an angle, does it? You can describe it like inverse cosine of 44 over root 32, 32, and so forth, but does that tell you how big it is? We're going to go to the next step. So we know the dot product, it's 44. We know these two, they multiply to root 32, 32. We don't know the angle. We are trying to find it. So I need a little bit more room, it seems. We're trying to solve for theta. This is in the way, and it has got to go. Cosine of theta is 44 over root 32, 32. What are you going to do next? Inverse cosine. Same as any other trig problem that you are given and asked to find theta. The fact that it's the result of several other steps is irrelevant. Bonus fact, cosine is invertible from 0 to 180 degrees. Because, and I'm going to keep saying this, technically, negative vectors are pointing in the same direction. It is impossible for the angle to be more than that. So we're good. What is theta, the angle between these two? What is theta that makes this happen? Inverse cosine, both sides, what's theta? I'm expecting 2 different answers based on whether or not you switched your calculator over to degrees or not, and I'll take either. It'll be pretty clear to me which one you did. It should be in radians, but a degrees answer will be fine for this demonstration. I see an answer in degrees. If you're still working on it, keep going. I want to see that confirmed. If you're working on radians, I want to see that also. 40 degrees is a pretty recognizable answer, and that looks pretty close. Now, Alicia's just given me about 0.7. 40 degrees is about a quarter, little less than a quarter of all the way around half of a circle. Half of a circle is pi radians. 0.7 is a little bit less than a quarter of pi. That looks like a good answer to me. It looks like those 2 answers agree to me. Hell, one of you switch your answers from degrees to radians or radians to degrees, and I'll bet you see the same thing. And more importantly, based on the picture, does that seem about right? Is there any reason to take 39 degrees, to take 0.7-ish radians and say, no, that's wrong, that can't be the right answer? I don't see anything wrong with it. It's clearly smaller than 90 degrees. It looks good to me. I say we run with it. Yeah, that's how it works. Angle between two vectors, boom, boom, inverse cosine. No weird stuff happens, and you're good to proceed from there. Now, because of the way that dot products are so geometrically based, and because of the components by which they're made multiplying down the line, dot products do a bunch of funky things. Some of which you might not think are funky until you remember, hey, wait, vectors aren't numbers. Vectors have no reason to obey the rules of numbers. In fact, they don't obey them all. But they do obey some when you think about the dot product. Here's one of them. What do you get when you take a scalar, such as 3 times a times b in regular variables? Do you triple the a? Do you triple the b? Doesn't matter, right? You triple the result. Works with the dot product. 3 times a dot b will be 3a dot b or a dot 3b. These are all the same. It kind of looks like that the associative property works. Well, as long as one of them is a scalar, yes. What else do we have? I already showed you this one. You can verify that on your own, but basically, since you're just multiplying by pairs, that's pretty poor. Let me try that again. There we go. That's better. What else? Well, as it turns out, the dot product also obeys the distributive property. You can add vectors. As it turns out, the dot product, let me make that clear, that is a dot product, effectively multiplies through. Think about it. If I was going to dot product B, I'm going to multiply A's components by B's components in order. I would do the same thing here. Does it matter whether I add the B and C components first or second? They're still paired up. Of course that works. Here's one that makes a lot of sense if you think about it. What is anything dot itself? Resist the urge to write that as squared. Remember, there is no such thing as times in vectors. So this is not a squared. And you'll see a big reason why not in Friday's class. But think about this. Isn't A going in A's direction? As it turns out, this is a number. It can be squared. Is basically the result. Think about it. What is the angle between A and itself? 0, right? Because A is itself. There is no angle difference. This is not a bad thing to have lying around. Don't let that wander too far away from you. But here's the big one. We've been talking about vectors and the angle between them, and it seems awfully similar to things like right triangles, but not all triangles are right. Give me a Y in the chat if you have ever seen this before. A squared plus B squared minus 2AB cosine theta equals C squared. Y in the chat if you've ever seen this. This is Calc 3. I'd like to see more Y's. I have, that's just as good. Now, maybe you haven't used it in a while, and I would understand that. This is the famous law of cosines. It's very useful for finding the angles of a triangle if you know all three sides. It looks kind of like the Pythagorean theorem, and if it's a right triangle, it is the Pythagorean theorem. And if it's not, it still works. But what else have we seen with cosine vectors? Just saw it today, but it's still there. Here, therefore, is the equivalent projected into the world of vectors. If I have vector A and I add vector B, I create vector A plus B, and I create a triangle whose angles we can find. We just did one. But we can go one step further. Which of these three is the longest side? Well, here's the thing. Judging by the picture won't give you the right answer. Truth is, you don't know. If I ask which of the three sides of a triangle is the longest, you need more information than that. I drew these, but couldn't I have drawn these? Here's A. Now it's really A. Here's B. This is still A plus B, but isn't that the shortest side of them all? The final thing that we're getting from this today is, again, an extension of what we just saw about cosines involving the dot product. Now, this formula doesn't actually have a dot product in it, but we're putting it here because it came after the relationship between the law of cosines and what we did see kicked in. What do we know about this side? Not a ton, but we do know one thing. Maybe it's the shortest side, maybe it's the longest side, maybe it's in between. We don't know, not without more details. But we do know one thing about it. It cannot possibly be bigger, than these two combined. This is the famous triangle inequality. And it basically says that no side of a triangle is bigger than the other two sides added, which is true. In a brief sentence, why must it be true? Why can't one side of a triangle be bigger than the other two added? Why must this always be true? Think of it more as the sides of a triangle than the vectors. That will help. Someone must have a thought on this. We've got like 60 seconds. By the way, if those of you are typing slowly on a phone because maybe you're just not as fast as typing with a phone as you are, and you think that all these typing out situations are a little unfair, don't forget, if you want to ask a question or if you want to verbalize an answer like this, feel free to basically say like "why" in the chat and then switch your mic on. That's fine with me. I'm not being phonist. It's just the chat is being saved and easy to read. So who has a thought? We're basically out of time, but I still want to answer this. Why must the triangle inequality work? Why can't one side be bigger than the other two added together? It doesn't have to be a right triangle, so not really, no. Exactly. Liam is right. If one side was so large that it was bigger than the other two combined, the other two couldn't reach each other. Exactly, they wouldn't connect. Vectors phrase it this way, but that's all it is. All right, we are out of time, but we're also out of stuff that needs to be done. What we did today is in chapter 14.3, but we have not done any word problems yet. We're going to come back and do all the word problems in a few days. So for now, I'm going to give you some mechanical problems. 1 through 16 covers a bunch of different stuff. Do any 6. And I also want you to do 21 through 24. And I want you to take a look at 17. This is a challenge. That's a real challenge. Give that guy a shot. Keep an eye on the Moodle site over Thursday. You might see some products and stuff show up as an exercise, and we'll pick it up from there next time.